Hello and good afternoon, AI for Robotics class. I wanted to address just a few questions that we have going into our next lab. And number one, what are the frames on a robot? Are they X, Y, and Z versus, quaternions? And we've been doing these transformations here for a couple of weeks, and we haven't really defined each individual frame on a robot. So let's take a look at the point cloud that you guys will see all the way over on this side. I'm using the Azure Microsoft Kinect sensor. So if you take a look at this, the frames, and above me here, you'll actually see a view frames command pulled from ROS that is running the race car simulation. And each individual one of these, from the SimPose and the base of the car, the camera length, the base footprint, the left wheel, the right wheel, every single one of them will have a reference point, right? So you have a Z, an X, and a Y. And these are kind of like those angles on Euler angles, each one, but in ROS it only deals in radians and quaternions, and there's a significant difference. For us, Euler angles are more understandable, and it's a good reference for decomposing rotations into individual degrees of freedom, like for kinematic joints on robots, just like you see here on my body with a base link and a bunch of individual links. But they had significant disadvantages when it comes to computation in computers, mostly on ambiguity and we call it the gimbal lock. So as the pitch approaches 90 degrees theta around, you'll end up seeing that it'll fail. And quaternions essentially is a 4-element vector which can be used to encode any rotation in the 3D coordinate space, and it has those advantages. So I like to visualize a quaternion. There's a couple famous YouTube videos where you're curling your fingers inwards. The IJK, these imaginary dimensions that are run parallel, 90 degrees orthogonal to each other, allow us to understand and compose, this one real element and then these three complex elements. So we further understand how these rotations are occurring, but we have to constantly transform these inside our code from quaternion to Euler angle and vice versa on the way back. Thankfully, the TF package actually does a lot of this for us, and we don't have to do all that math, which is really, really helpful. But I think it's important for everybody to visualize, and you can run this view frames command in ROS yourself, so you can see all the individual connections from the chassis to all the wheels and the steering hinges and the base link to each of the footprints and to the camera. And one of the other reasons this is so important, so let's say that your camera, the Intel RealSense D435, is imaging something, generating point cloud or using the laser for the laser wander for the rollouts. You have to reference that WRT with respect to the base link, and then with respect to the map, and then with respect to the odometry, and then with respect to the individual pixels on the map. So it's always with respect to, and then when you do that, you're going to convert it from Euler angles to quaternions, which is radians, essentially that 4-element vector that we're dealing with, okay? A few other things this week I wanted to address. Number one is referencing the localization node. We have to create this within our package for this lab, and I highly recommend going out and viewing the adaptive Monte Carlo localization package or nodelet manager. This has a lot of sample Python code that will help you visualize what's going on under the hood when you're attempting to localize for individual degrees of freedom, or allowing the robot to understand where it is in reference to the map. And that's very, very important. Obviously, if you're just creating a proof of concept, then you can just drag and drop this in there. That's very helpful. But for us, we're learning the fundamental concepts of PID, MPC, and localization, and we're actually coding that from scratch. So it's a little bit more challenging, but it's going to behoove us in the end, because we're going to understand all the theoretical concepts that are going on in real time. And it'll help us design systems that are more computationally efficient moving forward. And number two, I think one of the other things when we're attempting to calculate the derivative error for the buffer error, that 10-element NumPy array, do not calculate or compute the delta based on a max or min or an average. You essentially have to summate or summation, n plus 1 plus 2 plus 3 plus 4, and the polarities will actually cancel each other out, right? So if you're driving this way and this way, the angle will go slightly negative, the theta will go slightly positive, and at the end, because it's first in, first out in that buffer array, it'll essentially balance that out. So when you design your PID, it's not doing this, or the magnitude gets too great and it ends up going in circles. Okay, so I hope this has been a little helpful for you to understand the significant differences between the Euler angles and quaternions. For me, I spent a few days just wrapping my head around all the different equations and calculations that the TF package is actually doing for us, because the math is slightly complicated when you're attempting to multiply these matrices together and then do the conversions. But again, the TF package in ROS does all of this for us, thank God, and it's very, very, very helpful. So thank you guys so much for tuning in. I really appreciate you always tuning into this channel. It means the world to me. And if you have any questions, reach out and let me know. Have a wonderful day.